Welcome to The Explainer. You ever stop and think about what's actually inside your phone? Like deep inside? Today, we're going to pull back the curtain on Verilog. It's basically the language used to draw the blueprints for the billions, billions of tiny switches inside every microchip.
I mean, how in the world do you even begin to design a chip with billions of components? It's just staggering to think about. But here's the thing. Before you can build anything that complex, you need a plan, right? A blueprint. And for digital electronics, that blueprint is written in a language, and that language is Verilog.
Okay, so here's our game plan. We'll start with the big idea, this concept of thinking in hardware. Then we'll introduce Verilog itself and its basic tools. After that, we're going to get our hands dirty and actually code a simple circuit. And finally, we'll zoom out and see why this all matters so much. Sound good? Let's jump in.
All right, first things first. We have to get our heads around a really core concept. Verilog isn't like writing normal software that runs on a computer. No, it's about creating a super detailed description of a physical thing, in this case, the computer chip itself.
And that's exactly why they call it a hardware description language, or HDL for short. You're using it to literally describe digital hardware. I'm talking everything from a single tiny logic gate all the way up to a massive microprocessor or a chunk of RAM.
Okay, so this is where things get really interesting. Using an HDL requires a totally different way of thinking compared to a typical programming language.
So check this out. Think of a programming language like Python or C++. That's like giving a chef a recipe. First chop the onions, second heat the pan. It's a sequence of steps. But Verilog, that's like handing the chef the actual architectural blueprint for the entire kitchen. It describes the oven, the fridge, the plumbing, the electrical wiring, everything existing and working at the same time in parallel. You're not writing the recipe, you're literally designing the kitchen.
So if you're going to describe these circuits, you're going to need a toolkit, right? Well, in Verilog, your tools are called operators, and they really do work just like tools in a digital workshop.
First up, we've got the ones you probably already know. Arithmetic operators for your basic math and logical operators. And these logical ones, and, or, not, they are the absolute bedrock for making decisions in your circuits.
Then you've got relational and equality operators. These let us, compare things. Is this signal higher than that one? Are these two values equal? Asking these kinds of questions is how you start to build really smart hardware.
And this is where you can really see the hardware focus of Verilog. Bitwise and shift operators. These let you get in there and manipulate the individual ones and zeros, the actual bits that are flowing through the circuit's wires. This is where you really get down to the metal, so to speak.
Okay, enough with the individual tools. Let's see how they come together to build something real. We're going to dive into what's called gate-level modeling. And honestly, the best way to think about this is like building with digital Legos. Each little brick is a basic logic gate.
So pretty much everything in Verilog is built using something called a module. A module is basically a self-contained circuit. It's got its own inputs and outputs. Think of it like a little black box that does one specific job.
And building one of these modules always follows the same 4 steps. It's a really clear structure. 1, you declare it, give it a name. 2, you define its ports. That's the connections to the outside world. 3, you describe all the internal wiring and logic. And 4, you close it out. Simple as that.
All right, enough theory. Let's actually put this into practice. We're going to build a simple circuit that solves this logical equation right here. Y equals A and B, or C.
Okay, let's do this. We start with the module keyword, and we'll call our creation simple circuit. Then we define its connections, the ports. We need 1 output, which we'll call Y, and 3 inputs, A, B, and C.
Okay, now for the inside. We need to define the internal connections. To do that, we declare something called a wire. Let's name it W1. And this is a really important concept to get right.
See, a wire in Verilog isn't like a variable in software that just stores a value. No. It represents a literal physical connection that's going to carry an electrical signal from one component to another. It's the digital glue that holds our whole design together.
So now that we have our wire, we can instantiate our first logic gate. That just means we're creating an instance of a pre-built AND gate. We'll give this specific one a name, let's say G1. Then we just wire it up.
Its output connects to our internal wire, W1, and its inputs get hooked up to our main circuit inputs, A and B.
Next up, we need an OR gate, so we'll instantiate one of those and call it G2. Its output, well, that's our final destination, the main circuit output Y. And what about its inputs? We'll connect it to our third main input, C, and, you guessed it, the signal coming from our AND gate, which is being carried perfectly by our internal wire, W1.
And to finish it all off, we just type end module. And that's it. We've done it. We've fully described a physical hardware circuit. It's kind of wild to think that from this simple text, a machine can actually figure out how to lay out real transistors on a piece of silicon.
So, okay, that was a pretty simple circuit. But why is learning this basic structure so important?
Well, what we've just done is basically the atomic unit of all digital design. Remember that crazy chip with billions of components we mentioned at the start? Well, it's built by connecting millions and millions of tiny modules, just like this. A simple adder, a block of memory, the core of a processor. They all start with these fundamental descriptions of gates and wires.
So, you've just learned the basic grammar of digital blueprints. You've seen how a few lines of text can describe something that will become physical transistors. The only question left is, what are you going to design next?